So let me give you the following definition. We talked about this via example, sort of informed by last time. Let me give you something a little bit more concrete. We're talking about these quantifiers here. Let P of X something like x squared equals 4, something where we don't know the veracity of it until we plug in for our variable x, whatever that may be. One, the sentence, we'll write this in quotes. There exists an x such that P of x is true. Something like this way. There exists x of x. By the way, when you all do proofs for me in this class, I write this down because this is kind of the formal notation that logician might use. You can write there exists, in fact, I prefer, at least for most of it, for you to write it in English. I will use symbols like this, but I won't write these so compactly. This is just to introduce you to the notation that you might see. Is true. So when is this true? There exists x such that P of x. When is this true? This is true when the truth set for P of x is not empty. So there is some x in the universe that you happen to be living in that makes this statement true. There is some x that makes P of x. Sometimes we call there exists, this backwards E, an existential quantifier. The sentence for all x P of x sometimes this way. This means well, when is this true? Is true if P of x is true for all x in our universe. And the upside down A for all is sometimes called the universal quantifier because it's true for everything in the universe. So let's look at an example. We talked about this last time with respect to ambiguity, but let me give you some sentences here. Let's look at this one here. How might we write this? Here's something that you might for any two. With any two rational numbers is an irrational. So this is just something. How many of you have heard this before in your travels? That between the two rational numbers. You have heard this or not? Okay. We need to clear this up a little bit. First of all, what's a rational number? Yes,
A number that can be expressed as a whole number or a fraction of the numbers.
a rational number is a quotient of two integers. 5/7 minus 3/8, right? Any integer is a rational number because an integer is an integer over one, right? Do I agree with that? Can somebody give me an example of something that's not a rational number? I'm sorry. Root 2, actually, I'm going to prove that for you later. But how many of you are aware of the fact that square root 2 is not a rational number? Pi, e, these are all examples of irrational number. Between any two rational numbers is an irrational number. I did not say it here, but what are you supposed to be an appropriate universe? Consider this. The real numbers, right? So I'm going to take the universe here. What happens to the statement if my universe is the rational numbers? Actually, if my universe, if I consider all numbers just to be the rational number, this is not true, right? Because by definition, everything in between two rational numbers is rational, because I'm throwing out all the irrationals. It's not my universe, right? That's why it's important that I consider my universe to be the real numbers. Otherwise, this statement doesn't really hold water, right? How can we express this? Is this a universal or is it existential? This statement about there being an irrational. It's existential. This does not say between any two rational numbers, everything's rational. It says between two rational numbers, there's at least one irrational, right? So let's see, what's a good way to state this? We could write this as and there's not a unique way. In fact, I'm going to do another example, I'll do it in a couple of ways, but okay, this sort of sets the tone. For all A, B, and Q, what does this mean? This means for all A and B are elements of Q. This means contained in there, that little lowercase e looking thing. This really says that if A and B are the same rational numbers, there's nothing between them. So I'll take A to be less than B. Implies that there exists a real number there exists C, and we'll say that C is in R. Here. Between A and B, I can find C, there exists C. So C is real, right? Notice everything up to this point could have been in the rationals. This expresses the fact that we're living in the real universe. And C is not in say this. Oh, double up on those answers. there's a C that's real and it's not rational. And what else do I need it to be? I need it to be between A and B, right? So I'll add this on. A less C less. So read this. For every pair of rational numbers, if they're different, we'll say A is less than B, then there's a C that is real, not rational, and between A and B. Everybody okay with that? I want you to be able to read this. When you do the homework, please don't write it this crappy way. Just say that there's something between them, right? Unless you really, really hate my guts, then you can do that. Yes. Right. This sets the tone. A and B are rational numbers. This really means A and B are different, right? Because if A and B are the same, there ain't nothing between them, right? If A is less than B, then there's a C that is real, that is not rational, the irrational part, and it's between A and B. Okay. Okay, how about this one? This is kind of an Archimedean property we'll talk about later. Here's another statement we can try to put in fancy terminology. How about this? For every natural number, there's a real number that is larger. So if I walk up to you and give you any natural number, 1, 2, 8, 6, 7, 5, 3, 9, you can find a real number that exceeds this in size, right? Everybody agree with that? How could I write this formally? Well, I'm going to do this actually a couple of ways. For all natural numbers, and this is the symbol for the natural numbers, which I will call for your just positive integers 1, 2, 3, 4, forever and ever. For every natural number, yeah, so there exists R real number, such that R is bigger than N. That's kind of a compact way. Another way, which is the same, which is sort of in keeping with the way that I wrote this statement. For all N, if N happens to be a natural number, then there exists R such that R is an R and R is bigger than N. So there's a couple of ways that you can write this more formally. It's good for you to be, again, like I say, it's good for you to be able to read this. But you know, I mean, I don't even write this way myself anyway. I'm not a magician, actually. Yes. I thought you're talking about this one right here.
Yes.
Is that correct?
Yes.
So that's actually for your convenience. I've got posted on my webpage and also on Canvas. You can look at. I've got a list of symbols that I use. This is one of them, and I think I didn't mention this today, but if I have, this is his a member of. And we'll get to this when we talk more formally about sets. So for example, two is an entity. That just means this lives in this set. Okay, other questions? Yes.
So for example, 1.3%, like for like the statement under it, the universe to be blown up, like that statement, you said it was false.
Right, if my universe was just the rational numbers,
Oh, just the rational.
if it's just the rational
Okay.
numbers, then this statement is false.
Okay.
Right. Okay. So, definition. And I think that this probably won't, this is an appropriate definition here. Two quantified sentences like the ones that we just dealt with that have quantifiers in them, are equivalent in some universe they're equivalent in the universe. I'll call it U, and the U may be the natural numbers, it may be it could be real numbers, complex numbers, it could be the Fargo landfill, any universe where you can talk about there exists a piece of garbage in this landfill. Anytime that you can talk about quantifiers, we say that two quantified sentences are equivalent in this universe if they have the same truth values. Two quantified sentences are equivalent if they are equivalent in all universes. So really, from a practical point of view, we focus on the first one because usually I'm going to be talking about a specific universe, right? We're going to be doing problems. We're going to be in the real numbers, we're going to be in the rational numbers, we're going to be in some collection of matrices, whatever it is. But there are quantified sentences that are equivalent in every universe, right? Given any sentence, it is equivalent to itself in every universe. So for example, the statements there exists X such that X squared equals 4 and there exists X such that the absolute value of X is 2 are equivalent in any universe contained in R. Um. There are other universes where this may be ambiguous. For example, if my universe is 2x2 matrices with entries in the roots. The first thing I've got to do is figure out what I mean by 4, right? What does that mean for a 2x2 matrix? Maybe it means 4 times the identity matrix. But the bigger problem is, what do I mean by the absolute value of the matrix? Right? And in fact, there are often lots of, well, algebra can get very strange for matrices. Now consider universes for these two statements. So continuing the example. For all x is bigger than 3. 2, for all x is greater than or equal to 4. If somebody give me give me an example of a universe in which these two statements are equivalent. Yes. Okay, sure. How about another? Yeah, insurance. How about another one? Well, I'll give you another. Yes.
What about you as the like? I guess you call, I forgot what you call it, whether it's like finite or cyclic.
Oh, right. Yeah, I like you thinking out of the box here. The problem is with the kind of example we did last time is the greater than or equal to, that's not really well defined. But let's look at some other differences. Look at the left half of the real line. What's the status of this statement in this universe? This statement is false. Right? Always false. What about this one? Always false. How about this one? Right? In this universe, this statement is always true, and so is this. So they're equivalent. Give me a universe where they're not equivalent.
Are
Okay, right, that's sure. Not equivalent rationals either. Okay, any questions? Okay, so here's one, maybe you can help me finish this theorem. See if we can fill in the blanks here. Theorem, uh, if P of X is an open sentence, then, number one, not two. Uh, yeah, and these hold in any universe. Okay, let's take apart the first one. For all x, p of x means for every x in the universe, p of x is true. What is the negation of that? So it's not true that every x makes it. So what's that mean? Yes,
Here exists x such that p of x is false.
I agree with that. There has to be at least one where it's false. So this is equivalent to there exists x. Not p of x. Everybody agree with? So the negation of this, the statement for every x is true. The negation of that is there's some x for which it's not true. Everybody agree with? How about the negation of this? At least one x in the universe, p of x is true. What's the negation? So the original statement before we negate it is, in the universe, there's at least one x for which this is true. Maybe all x, but at least one. What's the negation of that statement? There's not a single x in the universe that makes that work. Everybody agree with that? Let me write that down carefully. For all x, not p of x. Like, okay with that? For all x, p of x doesn't work. Right? Okay, any questions on that? Okay, so let me give you a definition, another definition. This is kind of a notational definition, if you will. There's another, when you have there exists, there's another important descriptor you can put onto this. For an open sentence, facts. We can go a little further than that there exists. The statement I've got that exclamation point here. This is read, there exists a unique X, which would be of X. Uh, there exists a unique, and that's the exclamation point, X, such that this is quite important in mathematics as well. How many of you have had differential equations? Right? In differential equations, at some point, did they talk about, they might not have gone too deep into it, but they talk about existence of solutions and uniqueness of solutions, right? So when you solve a differential equation, you want to make sure that you've got a unique solution. You got to find that unique, because I ain't getting on anybody's space shuttle where they say, oh, there's two solutions to this differential equation. One of them involves you getting safely to space, and the other one involves you blowing up into a pile of ash. I want to know that there's one solution that's going to get me safely to wherever I go, right? So this is important, and this notation means there exists, not only does there exist an x, but there's only one x, which p of x is true. And this is true. Here. Only if the truth set has a unique element. So there's an answer to this, and there's only one of them. And we often call this, there exists exclamation point is the unique existence quantifier. Okay, so let me write down this theorem, and then I'm going to give you kind of a table of some equivalents, more important, some tautologies. Theorem. Let P of x be an open sentence. The following all are true. Number one, okay, so this is the first one, and this isn't shocking, right? What does this say? This says if there's a unique x such that P of x, then there exists an x such that P of x, right? Not a surprising. This is the stronger statement, right? Both of these mean that there exists x P of x, right? This one just means there's only one of them. So when you have this, you have to have this. Do I agree with that? That one's not too difficult, I think. Number two, there exists x P of x. Oh, I'm sorry, there's D. There exists unique x P of x is equivalent to simply to kind of talk our way through this. There exists unique x P of x. What is that equivalent to? Well, you certainly need this. So let me. I'm not done, right? These certainly, this is a stronger statement. This is only one answer. This is one or more. What do I need? I need more conditions on this orange. I need to sort of dial this back so that there's only one, right? Any ideas on how to do this? So I'm gonna put an and, I'm gonna add another condition. And for all y and for all z, uh, p of y So what does it mean to have a unique P of X or a unique X such as P of X? Well, you have to have an X such as P of X, and this condition is trying to get the uniqueness. So for every Y and Z, such that P of Y and P of Z, this should imply what? Everybody see it?
That's why it's just.
Good. So this gives you a solution. This part gives you the uniqueness. For every Y and Z, such that both P of Y and P of Z are true, that means Y and Z had to be the same. That means that there's only one. Right. Any questions on that? See, yes,
So P and Y and Q and Z are like, would be the same quantifier, just like different variables?
right. So if these are, for example, right, so if these are both true, then these have to be. Right. Now, I'm gonna go through some of this a little bit more carefully. This is, I know it's a little bit hard to see at first, but I am going to give you a list of several, maybe close to a dozen, list of what we call common tautologies. Somebody remind me what a tautology is? I remember that.
It's always true.
It's always true. So if it's made up of different propositions, no matter what the truth values are of the propositions, where you make it true, false, willy-nilly, the entire statement turns out to be true. A good example of this is Jim is happy or Jim is not happy. Whether I'm happy or not, that statement is true. Everybody agree with it? I'm going to give you a table of some basic tautologies. And these tautologies, since they're always true, are actually basically they're by the way, as we start this, because we're getting kind of warmed up to doing this part of proofs, let me ask you all these. How many of you have ever seen a proof done? Okay, so where did you see it done? Let me rephrase. How many of you have seen a proof done outside of a high school geometry class? Where did you see it? I'm sorry? Okay, textbook. Did anybody prove anything in calculus?
Yeah, to do proofs and calculus.
Right, like a standard thing that they might have shown is if you have a differential function that's continuous, something like that. We'll go through this. Now, these tautologies basically give you the logical structure for how proofs work. I do not, this is not a high school geometry class. Did you all have to do those proofs when you were in high school where say you fill in the little blanks? Oh my gosh, it's like, I just rather run my tongue over a cheese grater. I mean, that's awful. No wonder people are afraid of this class, right? But proof is art. And it's not just art, it's understanding. Because basically, when you do proofs, you're getting up under the hood, you're understanding how things really work. Lots of good new results come out of doing this. But at the outset, I'm going to tell you what these basic tautologies are. And we'll use them, although we won't sit there and fill in boxes and quote this. I'll even give you kind of some of the fancy names. And name if I ask them. So let's start off with this one. This is the one that I just said. P or not. This is a tautology because it doesn't matter if P, since this is an or, if P is true, then this thing is true. And if P is false, this is true and the whole thing is true. This is called excluded middle. You're either one or the other. You're happy or you're not happy. Here's another tautology. P implies Q. If and only if not P, or I'd say not Q, implies not P. You all might know what this is because we've already shown this one. Do I know what this one is? What's the relationship between these two statements? This is the contrapositive. How is this useful in a proof? How is this useful in a proof? Well, one thing that you can use the excluded middle is, since this is always true, if you want to prove P, then all you have to do is show that either P or not P is true, right? And so if not P is false, then P has to be true, right? This one right here is useful because you might want to prove that P implies Q, right? Like you might want to prove that every Lexus is a car, right? It might be easier to prove that if you don't have a car, you don't have a Lexus, right? And so this allows you to, instead of going this way, to prove not Q implies not P, and sometimes that's easier to do. P or Q or R is equivalent to P or Q or R. And P and Q and R is equivalent to P and Q and R. This one, anybody know what this one's called? This one sort of mirrors some things that you may have seen in other parts of math. This is called associativity. It doesn't matter when they're all ands or if they're all ors. It doesn't matter how you associate them. We have another pair, P and Q or R is equivalent to P and Q or P and R. And there's an analog, P or Q and R is equivalent to P or Q and P or R. And this one, anybody know what this one's called? Good, this is primitivity. And I proved, I don't remember which one, but I proved one of those earlier. And how did we prove it? We compared the truth tables, right? Here is continuing table here. This is P if and only if Q. And this is equivalent to P implies Q and Q implies So the double arrow, the if and only if, means P implies Q and Q implies P, and this is by condition. Um, P implies Q not. We've actually shown this one earlier as well. I think we did a truth table on that. This is equivalent to P and not Q. And this is called denial of implication. And of course, I see where these two names come from. By means it goes in both directions here, P and if and only Q. And denial of implication, that's exactly what you've done. You've denied, actually negated, P implies Q. Here's two of them right here. Anybody remember what not P or Q is? Well, right. How do I link them up? And good. And similarly, not P and Q is not P or not Q. And these are called the Morgan's laws. I've just got a few more. This one is called contradiction. P is true if and only if not P P is true if and only if not P implies Q and not Q, right? This is called contradiction. I do a lot of proofs by contradiction, but I don't sit and think of it in this term. Let's kind of talk through contradiction a little bit. What can you say about the status of Q and not Q? Always, it's always false, right? Q and not Q. This is always false, right? So what's the only way that, if this is false, what's the only way that this can be true? You need to have not P be false. And if not P is false, then P is ding, 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 right? So that's essentially why contradiction works. P implies Q and Q implies R implies P implies R. This is called transitivity. If P implies Q, Q implies R, then P must imply R. And finally, this is actually the first one we saw. P and P implies Q. And this is modus ponens. Okay. Questions on that? I am going to leave you because I can't, we're going to start into really getting our hands dirty and going through proofs. I'm not going to formally go through this, but remember these tautologies. And I think the best way to go about this is trial by fire and be doing lots of examples for you. But I'm going to give you the final proposition that is going to be central. And this is actually equivalent to induction, which we will study later. Every non-empty subset of the natural numbers has anybody, does anybody know, this is one of the most important theories in the basics. If I have any subset of the natural numbers that I want, any subset that has at least one element, anybody know what's special about that set? This will probably appear. Does this make sense to you intuitively? That if I take a subset of the natural numbers, as long as it's not empty, all I have to do is sort it out and find the smallest one. And there's the smallest one. Okay. This is equivalent to induction in the study later. We're going to use this. Any questions? All right, y'all have a good one, and I will see you on Friday.